here. Okay. So it's basically word problems involving second order differential equations. So we're gonna do spring problems. Okay, that's about all we're gonna do is the spring problems. But like this is section 6.1 and 6.2. So spring problems. Okay, and let me just show you the situation here. You have some support here like this, and there's a spring hanging down. This is the spring. Okay, and the spring has some constant, a spring constant K. Okay, there's one called Hooke's law. Okay. Okay, but it's from physics, I guess. There's a spring, it has a spring constant, right? So the spring has a constant, like the stiffness of the spring. Okay, and then there's a mass hanging from it. Okay, so some sort of mass hanging from the spring here, like a block of some sort. Okay, and then also in this too, there's also something here called a dash pot. Let's say under us like this. This is kind of a model for it here. But basically what this is, it's like a viscous liquid of some sort. Basically, it accounts for friction. So the faster the mass is moving, right, it's the resistance is proportional to velocity. So this gives you like a resistance to the motion. Okay, it's proportional to velocity. So imagine like a viscous liquid or something here. It acts like a friction, basically. It's how you can account for friction. Okay, in the spring or whatever. And let's say this has some constant here. There's some constant C associated with this. So it's like some constant here. C with that. Depends on how viscous the liquid is there. Okay. Now, one other thing here. If the mass is just hanging here, okay, if the mass is just hanging there, it's like an equilibrium. Okay. And let's say there's a position here like this, the equilibrium position. And the distance off of equilibrium that it is, let's say this is y here, like that. That's called the displacement. Displacement from the equilibrium position. With the mass hanging on it there. Okay. Okay, so one thing about this, if the mass is just hanging here like this on here, right, it's an equilibrium then. So that is displacement 0. So if the mass is hanging there and not moving, that's displacement 0. The spring's actually stretched a little bit when that happens because the mass stretches the spring. But we're assuming if there's no motion, if it's just hanging there, that's displacement 0, even with the mass hanging on it. Because it's actually stretched a little bit the spring, but it's just sitting there. Okay. And also say then there's some other let me say here, we'll account for this. Also, let's say also suppose there's some external force in the block. Okay, so this is kind of the picture here then. So, right, so you can imagine if you pull down the mass a little bit, it will start to oscillate, right? It will oscillate up and down then. If you pull down the mass a little bit and then let go of it, okay, it'll go back and forth. And if it's viscous there, it'll dampen out then. It'll eventually slow down and stop because of the viscosity there of the C. Okay, that's like the friction part. So if there's no friction, it would just oscillate forever, right? If the friction weren't there, it would just bounce up and down forever, the spring. Okay, now basically the equation of motion then, right? How the mass is going to move, it's given by this. So this is the differential equation here. Okay, this is the key equation right here. I'll put this in the box. Okay, for the motion of the spring. So it's the second order differential equation here, like that. Okay, so anything there so far? So we'll kind of work through a problem here and see how this works a little bit. And the idea is we want to figure out the y as a function of time, right? So you're given some initial conditions. You want to figure out the displacement as a function of time of the spring, of the mass there. Okay, so let's try this problem here now. Okay, and released. And this is the acceleration of gravity here. You have to have the acceleration of gravity for this actually here. Oh, and also here, let me say also here, assume that C is equal to 0, so there's no friction, and F of t is equal to 0. There's no external forces. Okay, so this is the problem here then. Okay. Now, by the way, this external force right here, this F of t, that'd be like if there were some other forces on the spring here or on the mass. Like you can imagine like a little thruster on the mass here. So if there's some other force acting on the mass as a function of time, like say a little thruster on it or something, whatever it is, that'd be the F of t. If there's some other external force on it, aside from the gravity. So, okay. But anyway, here, so look at this here then. So we're assuming here C is zero. That's the friction part. And then F of t is equal to 0. So right away, how's it go then? So my equation looks like what here? I get y double prime plus ky equals 0, right? With those assumptions there, right? No external forces. And you get this here then. Okay, and we also have here too. Well, we'll come back to the initial condition in a little bit, but we'll come back to the condition in a bit here. But actually, let me write it down here. I guess I'll do this now. What would be the initial condition? So y of 0. Okay, so initial condition. So the initial position of the spring. Okay, so it's pulled down 2 inches. Okay, and then released from the equilibrium position. Okay, now actually, we want to find the displacement in feet here. Okay, so the initial condition here would be like this. Okay, so at time 0, the displacement it's 2 inches down from initial position, from the equilibrium position. But this is going to be in feet though for the displacement. So we have y of 0 is equal to this. Okay, and the down is because it's negative. Like in the picture here, right, up is positive y and down is negative y. Okay, so if I take this and pull it down 2 inches, pull this down 2 inches and then release it, okay, initial displacement would be negative 2 over 12 then, if it's in feet. Okay, so anything there so far? This one? Okay, from right here. So it's pulled down 2 inches from equilibrium. Okay, so if it's resting, right? So it's resting. So the object stretches the spring 6 inches. Okay, and then now once it's stretched, that's the equilibrium position. So that's y equals 0. Okay, and then if you pull down an additional 2 inches from equilibrium, So you're pulling it down 2 inches from equilibrium. Okay, that's the -2 here, down 2 inches. But the displacement, we want to find it in feet. Okay, so you got to express this in feet. Yeah, that's the initial displacement would be -2 over 12 feet. Because it says in inches here, it's pulled down an additional 2 inches. Okay. But the equilibrium is the weight's already on it. So yeah, if it's equilibrium, that's y equals 0, then you pull down 2 from that. Okay. We'll use the 6 here in a minute, by the way. Like you might wonder what we do with the 6. Okay, but we'll see here. Okay. Now, if you look at this here, it seems to be an issue with this though, because what you notice here, I don't know the m, and I don't know the k, right? Neither one were given here, right? I don't know like what the mass is of it, and I don't know the spring constant. Neither one's given here. But there's actually enough information to do this, believe it or not. Okay. If you divide through by m, okay, you got y double prime plus k over m y equals 0. So you get this here. Okay. So now we still don't know the k or the m, so it still looks like a dead end, right? But here's the thing. Okay, by Hooke's law, okay, if think about the equilibrium here. Okay, right, if this is equilibrium right here, okay, so imagine equilibrium. Okay, so if it's equilibrium like this, okay, what would be happening here? From physics then, if it's equilibrium, there'd be a force down, right? That'd be the mg. That'd be like the mass times the gravity, or times the acceleration of gravity acting down. Then acting up here, okay, there's going to be some force from Hooke's law. Okay, and the force up is it's kx. Okay, where x is the displacement due to the weight. This has nothing to do, I'm using x instead of y for this part, but right, so but this is Hooke's law here. Okay, that kx there, that'd be the force of the spring. Okay, so at equilibrium, right, what do we know here? Right, so at equilibrium, right, if this is not moving, right, if it's at rest here, what do I know about the up force and the down force? If it's equilibrium, it's 0. Okay, so this is 0 here. Okay, so I know that mg is equal to kx, right, at equilibrium. So what you could do here then, you can actually solve this then. I could say, if I basically divide by m and divide by x, you can rewrite like this. Right, g over x is equal to k over m. I'm going to come back over here, right, the other way. So you end up with this thing right here, right? K over m is equal to g over x. And that's all we need here really is k over m. K over m in this. And we get that from g over x. Okay, so k over m here is equal to, now what's g? G is the acceleration of gravity. Okay, so that was given. That's the 32 feet per second square. So 32. And what was the displacement just from the weight? Right, the object stretches the spring 6 inches. Right, so you need that though in feet, because this is in feet per second square here. So this has to be in feet as well. 6 inches is like 0.5 feet. Okay, that's the displacement due to the weight. Okay, so 0.5 feet. So then k over m here is equal to, that'd be 64. So again there, right, really all you need here, you need the ratio of k to m. And if you know how this, basically it comes from this part right here, okay, in equilibrium. If the weight is sitting there, okay, if it's so stretched it, right, when it's just sitting there, then the weight of it has to be equal to the spring, the force of the spring up, right? So this is kind of key thing right here. So then really all you need, if we can get k over m is equal to 64 then there. Okay. And that's the part that goes right here, right? So we didn't know either one. We didn't know the spring constant. We didn't know the mass, okay? But we was able to find the ratio because we knew the displacement, okay, just from the equilibrium. Okay, that was enough to actually figure it out. Okay, so it's the ratio of the two. It's really important. Okay, so back to this then, right? So now we have this y double prime plus 64y equals 0. And we have that initial condition, right? Y of 0 is equal to what did I say? Negative 2 over 12. Oh, we also need another condition, which I didn't write down either. Since we actually need two conditions here. There's actually another one here too. What would be y prime of 0? If I go back up here for a minute. Okay, so y prime of 0 would be what? 0, because I pull it down, right? That's like the velocity, right? The y is the dy dt. So initially, when I release it, the velocity is 0, right? So I pull the mass down and then let go of it. Okay, so initially velocity is 0. Okay, so displacement initially is negative 2 over 12, and then this guy here is 0. I used to be like you'd say like feet per second here for that. Okay, so that's another thing you would need here. Anything there so far? Okay, so now he's going to solve this. Okay, so it's a homogeneous constant coefficient equation here. So remember how you do that? You find the characteristic equation. Right, so that's r squared plus 64 equals 0. That's the characteristic equation. Okay, and then so you get r here. R is equal to, that would be basically plus or minus 8i. You get there plus or minus 8i for the r. Okay, so how does that look then? That'd be y equals c1. Remember when it's pure imaginary, how's that go? Cosine 8t plus c2 sine 8t, like that. So that's anything here so far? Okay. So this is displacement as a function of time. Okay, but we also have now these initial conditions. We have to apply the conditions now, right? Now, actually here, though, to apply the conditions, I have a condition on, let me write the other one here. That was 0. I have a condition on the y here, and also on the derivative, there's a condition. Okay, so what I'm going to do here actually to find the initial condition, to do this, now I'll take a derivative here now of this. So y prime then, this is for the initial conditions to get. So y prime would be what? That would be, so it'd be like negative 8c1 sine 8t plus 8c2 cosine 8t. Okay, like this. So you got that here. Now apply the conditions. So now I know what y of 0 is equal to the negative, I don't know why I picked that number, negative 2 over 12. So, or I could say negative 1/6, maybe there. Right, so I know then what? I get 1/6, so apply the initial conditions. Right, so then y of 0 is negative 1/6. I get negative 1/6 equals c1 times cosine of 8 times 0 plus c2 times sine of 8 times 0. So I get that negative 1/6 is equal to what here then? C1, right? Because this is 1 here, and this is 0 over here. Okay, so this is equal to C1. So I know C1 is going to be negative 1/6. Okay, and then C2, from the other condition, I get 0 equals negative 8. I'll just put times C1 for a minute here, times sine 8t, or I'm sorry, that'd be sine of 8 times 0 plus 8 times C2 times cosine of 8 times 0. So that's applying the other condition into the derivative here. Okay, so 0. Yeah, so this one, what, would just drop out here then? Oh, wait, C1's negative. Yeah, okay. So then, wait a minute, let's see. Oh, okay, yeah. So I get here 0 equals, this would drop, right? This drops out here. 0 equals 8, C2, like that, because this is 1 right here. So what would be C2 then? Right, C2 equals 0. So C2 is 0 then. Okay, so what we have here then, what, y of t is equal to, that'd be C1 was negative 1/6 cosine of 8t, and that's it. Okay, so it'd be negative 1/6 times cosine 8t. Okay, that would be the answer here, because that'd be the displacement as a function of time. Okay, so any questions on that? Okay, if you graph it out, okay, it would look like this. If you make a graph of it, it would go like this here, and it'd be like a cosine wave. Okay, but this would be like this is time here, and this is the displacement y. Okay, so it'd start below equilibrium, and then it would go up, and then back down, and then back up, and then back down. Okay, like that. So anything on that? So it just oscillate down and up like that. Okay, which kind of makes sense physically if you did that. So anything on that one? Okay, let's try another one here. This will be a little bit easier, I think, now because we've done an example. But let's say here, let's try this now. Okay, so let's try this one here. So same situation, except this time we push the mass up from equilibrium and then give it a yank, give it a little downward velocity to start. Okay, and then see what happens to it after that. Okay. So again, same equation here, right? We got m y double prime c 0, so I can just drop that off, and then plus ky equals 0. So let's start with that. Okay, maybe I'll try to write down conditions here then. So what would be y of 0? And this time everything's in centimeters for this one. Okay, y of 0. Okay, initially it says the spring is pushed up 2 centimeters. Okay, from equilibrium. So it's at rest there initially, and then you push it up 2 centimeters from equilibrium, 2. So y of 0 is equal to 2. That'd be like 2 centimeters there. And then, now we want this in centimeters this time, so I'm using centimeters here. Okay, and then y prime of 0, that's the initial velocity, would be what? Well, okay. And given a downward velocity, yeah, except it would be negative because the convention is display. Yeah, negative stuff's down. Okay, for this. Okay, so that'd be -3 centimeters per second. Right. Okay. So anything on that so far? Okay. And I'm going to make myself a note here real quick. Something. Let's see. Okay. So see what this here then. Now, next thing then, I divide through by m here on this. So we get what? Y double prime plus k over m y equals 0. Again, here in this word, we're not given the spring constant. That's not given. We're not given the mass either. Okay, but really, it's just the ratio of the two that's important for this. Okay, because you just get k over m here. Okay, so now what for that? So remember, I'll just kind of jump to this then, right? So k over m is equal to g over x, like this, where x is the displacement from equilibrium. We're assuming it's positive here. Okay, it's just to get the spring, it's just to get the ratio of k over m. Don't worry about signs on it so much here. But the acceleration of gravity, that is 980. Okay, and then the m is, well, I'm sorry, that g is 980, and then the x, right? That's the displacement due to the weight. That was what? Yeah, 5. That's just how much it stretches it. So the spring constant, so k over m, right, it'd be like this, it'd be 980 over 5. And that is 196. Because that'd be the k over m for this one. Okay, so anything on that? Okay, so yeah, okay. So anyhow, got that. And okay, so now we get the differential equation here. So we got y double prime plus what, 196. Okay, y equals 0. I was just trying to think what would happen if there was no gravity. If g were 0, how would that work out? But I was just trying to think about that. But I should say that for another time. But let's see. So if g were 0, well, there'd be no displacement. Then it'd be 0 over 0, right? Because if there's no gravity, it wouldn't displace it at all. So anyway, okay. So that wouldn't make sense there. But anyway, it'd be 0 over 0. But anyhow, so you get y double prime plus 196y equals 0. Okay, so then what? So that means the characteristic equation is r squared plus 196 plus 196 equals 0. Like that. That's the characteristic equation. So you do this, you get r equals plus or minus 4. I think it's 14. Square root of 196 is 14. Okay, so 14i there. So y equals, otherwise you use quadratic formula or whatever and go through it. But so y equals what here? That'd be c1 cosine of 14t plus c2 sine of 14t, like that. Okay, now we'll take derivative here. Anything there so far? Okay, now we'll take derivative. So that would be negative 14c1 sine 14t plus 14c2 cosine 14t. So we get this here. And now apply initial conditions, right? So apply ICs. Okay. This time I won't write quite as much in this one. But what was our conditions? It was y of 0 was equal to 2, and y prime of 0 was equal to -3, I think. I think those are the conditions. So apply those. Now, if I put in 2 and 0 here, I get what? I get 2 equals, I think just C1. Right? If you use the first one, because I put 2 here, I put 0 over here. So this will drop, and this is going to be 1. Right? So just get 2 equals C1 from the first one. And then from the second one, that'd be what? -3 equals, and if I put in 0, that would drop, and I get 14C2, like that. So that's applying the 2 conditions there. Okay, anything on that? So so you get 2 here and 0 here, and then -3 here and 0 here. Okay, those. So then I get C1 is equal to 2, and C2 is equal to -3/14 C2. Or I'm sorry, -3/14. Okay, so then, right, y of t would be equal to 2 cosine of 14t minus 3/14 sine of 14t, like that. Okay, so that'd be the displacement there as a function of time. Okay, so anything on that one? Okay. And actually here, when you have like a sine here and a cosine, and these are the same. Like this is also going to be like a sine or cosine wave here, actually. It's like shifted around some and stuff, but it's really just another sine or cosine wave there. So this be it here for that. Okay. Anything there on that? Okay. And if you graph it, it looks something like, I won't put it in Desmos, but looks something like this. If you were to graph it, well, it would be like this. It'd be something like that. So that'd be so it'd be going down and up and then down and up and so on. Okay. This is it. This is it 2 here initially, right? And actually, I guess it'd be on the downward. It has an initial velocity, so maybe not quite like that. Maybe it'd be going down more like this. Something like that. Because initial velocities, it'd be like tangent line would be not horizontal there. So something like this it would be. Okay. Okay, so anything on that? Okay, I should fix my picture for next time. Okay. I'm fixing these up so if I teach this again, I'll have better notes. So I'm using you guys as guinea pigs to fix my notes as I go. So anything on that? Let's see. Okay. It's been a long time since I taught this one. And okay. My notes need better work. So okay. Is that one? How are we doing here? Okay, on to the next one here. Let's say now, say suppose M is equal to 5 kilograms, C is equal to 10 newtons per meter per second. Okay, K, that's the spring constant, is 45 newtons per meter. And say Y of 0 is equal to -1 meter. Y prime of 0 is equal to 0 meters per second. And external force here is, again, 0. So no external forces on it. Okay, I want to find y of t in meters. So and by the way, as soon as I put the c in here, this is like the friction part. Okay, or let me write down the equation here. So what that'd be? So basically, get this in 5y double prime plus 10y prime plus 45 y equals 0. So that'd be the equation here, like that. Once you have this, once you have a non-zero c here, then I have to give you the mass at that point. As long as c is 0 here, I could do what I did and not give you the mass. But as soon as you put the c in there, you need the mass at that point you need to know more about it. You need to know. Well, actually, well, yeah, because you divide it out, you get c over m at that point. If I did that before, actually, I'm just going to show you one thing here. I'll come back to that in a minute. But right here's the equation, right? Y double prime plus cy prime plus ky equals 0. Okay. Before, what I did there, I divided by m across here. Okay, and this wasn't here. It disappeared. This wasn't here before. So I just had k over m, and I was able to find that just from the Hooke's law. But as soon as I put the c there, now I end up with a c over m. Okay, and I'd have to know this ratio somehow. Okay, which means I'd have to know the c and the m, or so I'd have to have more information or something. Okay, but so you can't get away with it there as soon as you have a non-zero c. But anyway, but this time I gave you all the information there. So now the m is what? 5. That's the mass. Okay, and then the c is 10. And then the spring constant is 45. Okay, so we have that here. Okay, so now we need to solve this differential equation here then. Well, if you go through it here, basically I could write the characteristic equations like this, right? 5r squared plus 10r plus 45 equals 0. So I need to solve this here. Okay. So I could divide through by 5 across it, multiply it through by 1/5 on this. So you got r squared plus 2r plus 9 equals 0. I'm trying to solve the characteristic equation here then. So r equals, that'd be -2, right? Plus or minus square root of 2 squared minus 4 times a, which is 1 times c, which is 9, all divided by 2 times 1. Because you get this here. So r equals, that's going to be, if you go through this here, well, okay, -2 plus or minus, this is going to be 4 minus 36. Oh, wait a minute. Wait. Wait a minute. What happened there? Wait a minute. Let me check something. B squared minus 4 times a times c. Oh, okay. I guess I'll keep going. This is going to be what? That's -32 here. Is that right? Yeah, it's -32 all over 2. So r equals, and then that would be like -2 plus or minus. This is really like I square root of 32 over 2. And that's 4 square root of 2. Because 32 is 16 times 2, so you can take a 4 out of there. So -1 plus or minus 2 square root of 2I, like that. Actually, I'm just going to call it square root of 8. Well, whatever here. Yeah, I guess like this. So you get this here then. Okay, so anything there so far? Okay, so that's this here. And actually, I think it's going to be easier. I'm going to call it square root of 8. This here, if I put that back together, let's see, that would be, that's the same as square root of 8 right here, like this. Might be easier just to work with that, square root of 8 there. Okay, so then, so what would this be here then? So y equals, anybody remember how this goes then? When you have like the real part and the imaginary part there. Basically, you could write it like this. Let me do it like this here this time. You could say, yeah, it goes like this. E to the negative 1t, right, cosine of square root of 8t. Then e to the negative 1t sine square root of 8t. Like that. Does that look familiar, hopefully from a homework maybe earlier? Have you guys been doing your homework? No, okay. But this should, okay, I'll just say it this way. Yeah. So, okay. I don't know if this might have been due already. I'm not sure or not. I don't know. But anyway, take my word for it or look at the homework or a past recording. This is the same as this here. Okay, so that goes like that. Okay. Oh, I forgot something. My C's. There's a C1 and a C2 here. Should put those somewhere. I'll put it out here. C1 and then, my bad, a C2 like that. And actually, I'm just going to factor out the E there. So I can say E to the negative 1t. It might be easier like this then. Then cosine square root of 8t plus sine square root of 8t like this. Oh, I forgot the C's again. Darn it. C1 and C2 here. Because I get this here then. Okay. So any questions on that one so far there? This one's a bit messier because the roots are messier for the characteristic equation. A little bit messier here, but you end up with this. Okay. Yeah, now I'm going to have to find initial conditions. Remember, I get initial conditions here then. So I'm going to need to take a derivative. Okay. So y prime is equal to, now to take derivative here, how would you take derivative of this? Bit of a mess, but what do you got to do here? I'm trying to remember going after the conditions, the C1 and C2 here. So I need to get a derivative here. You have to use a product rule. Okay, the product rule for this. Remember the conditions. I'll write them back here. They were, well, y of 0 is equal to negative 1. Yeah, I'll write this over here just for reference. Right, y of 0 is equal to negative 1, and y prime of 0 was equal to 0. Right, those are the initial conditions there. You have to use the product rule to take the derivative here. So take derivative first part. So that'd be negative 1 e to the negative t. Then you keep the second part. A bit of a mess here. Plus, that's half of it. Now this time keep the first part, which would be e to the negative t. Now take the derivative of the second part, so derivative of all this now with respect to t. So that would be negative square root of 8 c1 sine square root of 8t plus square root of 8 c2 cosine square root of 8t. So that's from the product rule there. Looks like a horrible mess, which it is, or it's kind of a mess there. But some of us will go away from the conditions here then. But anything there so far? So that's using the product rule there, if I did that right. That looks right. Okay, so now applied initial conditions. Okay, so what happens here? And if you apply the initial conditions, I get y of 0 is -1. That's this one. So if I put in, so what I get -1 equals, hopefully things go away. This is 1. I put in 0. So 1 times, and then this here, if I put in, this will go, this stays, and that's 1 there. So I guess it's like C1 times 1. And then this part would go away over here. So you kind of get something like that from the first one. Okay, something like that there. And then now for the second one, so that's easy to solve. Then for the second one, then what I get 0 equals, I'm plugging this into the derivative here now, and you get, well, that would be -1 here. And then, oh, a bit of a mess. This would stay. This would go. Plus, and then that would be a 1. And then now this would go and this would stay. Actually, I did miss this. Okay. Did I miss a square root of 8 somewhere? No. Okay, this would go. This would stay. I think it's something like that. I should do it. I think that looks right. Everybody see what I'm trying to do there? I'm just plugging in the, it's a mess, but you put, you know, I'm putting a condition there. So you get -1 over here, and then put in 0 here. And then for the other one, you put in 0 here and put in 0 and all this. Get like this here then. So then from that, I get C1 is equal to -1. And so then I get 0 is equal to -1 times -1 is 1 plus square root of 8 C2. So you get like -1 over square root of 8 equals C2. Okay, so finally here, right, you get y is equal to C1, which is -1. So -1, what was it? -1. I put the e to the t outside. Okay, let me just do that again. So you get e to the -t. Then C1 was, what was C1? -1. Square root of 8t. Plus, and then C2, that was -1 over square root of 8 sine of square root of 8t, like that. Okay, so you end up with this thing here. Okay, bit of a mess. Let me check if that's what I got before. Yeah. Okay. Any questions on that when going through it? It's really just a bit of a mess. Any questions on the concept of it? I don't know if you were able, all the stuff there, it gets a little crazy, but the numbers and stuff. But let me go ahead and graph it. I'm gonna look at that in Desmos, see what it looks like. Okay, remember this is the spring where it's damped, so there's like some sort of friction or something. Okay, so let's just graph it out here and see. Did you guys write this part down here? I might ask about it in a minute when I put it in Desmos. But okay, so let me go ahead and stop this here. Okay, so consent and join. Okay, and okay, share screen. Okay, so what would this be? It was y equals, can somebody tell me about it a little bit? Y equals what? Okay, e to the -t. e negative t, and then times negative cosine of square root of 8. And the t's outside the radical. Just watch there. See it this, and then plus over square root QRT, okay, square root of 8 times sine square root of 8t. Now we only care about this really when t is greater than 0 here, because we had this at time 0. I set it in motion, so I'm going to restrict this here. Let's say 0 t's. Will it do t's? Is it doing t actually? I thought it just did x's, but did it actually graph it? Looks like it graphed it. Okay, I thought I made a mistake. I thought it only did x's, but maybe I was wrong on that. 0 less than t, I don't know, less than 5 or something like this, let's say. Okay, so this is what it looked like here then. I just picked 5 to see. Right, so this is what it looked like here then, right? So what this is, right, it's this place, right? It's this place below equilibrium, right? Y of 0 is -1, I hope. Yeah, Y of 0 is -1. It had no initial velocity, but it's in like it's like friction or something. So notice it goes up and it slows down, right? See, that's like that viscous liquid we talked about there, right? So it kind of goes up and then it kind of goes in like this then. So I want to try something. I'm just curious on something. This is just for fun. See if I can do this. Oh, I don't want to type it all again though. Can I do that? Well, let me. Let's try to make like a parameter here. I gotta think about that. 0. Well, let's try to get the animate here somehow. Like I was thinking I could put like a point down here. You think take out the 0 in front? I was thinking like an ordered pair. I was trying to plot a point. I don't know. I think how that would work. Yeah, I really don't want the line though. I wanted. Well, actually. Okay, t gets 0. I want to make like animation. Can I do a slider maybe? Maybe I want a slider. Can I? How would that work if I? Maybe put something defined here yet. Say like a C maybe? I don't know. Okay, this might be cool. I'll put a C here. Add slider. Okay. And now I want the point really big though. Let's make this point big. I'm just having fun here. Make the point big. Maybe 20. Okay. Big at 40. Let's see. Okay. And it's equal 0 to maybe 10. There. Okay. Now watch. Okay, watch this. This will be like the spring going up and down. So I think I can. Yeah. Okay. So there it is. That's like the. Well, I don't want to go backwards, but that's not supposed to happen. but yeah, whatever. You make it go. Can I make it? Oh, let's just do it this way. Can it repeat here? This would be cool. Let's see. That's what it would do, basically. So that's like the spring there, the dampening. So okay, any questions on that? So it's yeah. Okay. So okay. So let me switch back here then. Let's see. So stop sharing. Okay. So well, maybe let's see. always got to share back on this one, and but there we got that. Okay, any questions on that? Okay. Oh, one other thing I'll end up here real quick. It turns out you can classify spring systems when the f of t is equal to 0. Let me switch this back real quick. This won't take long, this part. Okay, so yeah. Classifying spring systems when f of t is equal to 0. Okay. The one we just did there, okay, that was called underdamped. Okay, this one we just did, where we saw it go like that. Like we just saw it there, right? It went like this. Okay, that's called underdamped. Underdamped. Okay, when it's like that. And basically, okay, you have these things here then. If C is equal to 0, okay, it's called undamped. Actually, I got to write down the equation here again. This won't take long here. So we have this here. If C is equal to 0, okay, it's called undamped. And it looks like this, right? The graph will just go, or go like, it'll just be like a sine wave or a cosine wave. This forever. It would go like this. That's called undamped. That happens when C is 0. If there's no friction, it would just oscillate. Like on that one I just did there. If the C were 0, it would just go forever, oscillating up and down. Okay. If the C is not equal to 0, and C squared minus 4mk is less than 0, okay, it's called underdamped. Basically, it's like doing the quadratic formula here. You get different kinds of solutions based on the discriminant, the b squared minus 4ac in the quadratic formula. That tells you if you get an imaginary or real number. Okay, if the square root's negative, if that, whatever that is there. So if this is less than 0, if you did the characteristic equation here, okay, if that thing comes out less than 0 there, then that's called underdamped. Okay, that's like this one. Okay, if c squared minus 4mk is equal to 0, okay, it's called critically damped. And this is if c is equal to 0 here. C is not equal to 0 here, too. Critically damped, that goes like, it goes like, say, like this here. It looks something like that. So if you dampen enough, it won't oscillate anymore at all. If you make the C bigger than it had it, it would eventually just, it wouldn't go back and forth at all. It would just go up like that and stop. So if you make the C big enough, it won't bounce back and forth at all. It will just go up and, okay, like that. That's called critically damped. Okay. And there's another one here. If C is not equal to 0, and this thing here is greater than 0, okay, then it's called overdamped. And that looks like, it's like critically damped, but it doesn't go as fast. It's more like this. Okay. The critically damped, this has a fast return, but it doesn't oscillate. It's the fastest return here. It's the fastest return to equilibrium. It's critically damped. And then if it's overdamped, okay, then it's actually a slower return to equilibrium. And so, okay, so fastest return, but there's no oscillation. Okay, but it does not oscillate. Okay, so it doesn't oscillate here. So that's some different things there. So I think there's a homework we have to classify them, okay, based on those. So those are the pictures there. So we did one of each. We did this one and we did that one. We didn't do this one. I guess we didn't do this one either. We did these two up here as examples. But it's just the value of, it's just these things here that matter then for that. And so, okay, we'll probably do one more next time. But anything on that? Okay, so we'll stop there for today. And then probably next time we'll finish this up and we'll probably start Laplace transforms next time, which is next chapter. So we'll probably start that on Thursday as well. We'll see, at least start on it.